class 11 and an example that I am going to walk through. This is example 5.1 out of Norton, and I encourage you to read the book as opposed to just listening to me. Remember what we have to remember what we're doing here. Is we're trying to synthesize position, right? We have these two positions, maybe A1 and B1, and we want to go to A2 and B2, and we're doing it by way of creating this point and figuring out the travel. So it's very similar to what we did right here, right? Remember when we had coupler output, where we're going to use that coupler output right here of A1 and B1 to A2 and B2 right here, so that we could generate something along these lines right there, if you'll recall. That's our main goal. And then once we've done that, we could also even add the driver in, right? So we could do this by way of analytically instead of doing it entirely graphically. So here's the 2 points that we want to go between A1 and B1 right here, and A1, B1, and then A2 and B2. So we start by establishing this point that we're going to go to between P1 and P2. And then so that the triangle that we're making A1, P1, B1 right here, and A2, P2, B2, these are things that are known. So if we measure we can measure or calculate the magnitude and angle of this P21. So let me pause just for a second and double check something. Here is selecting the point P. I suppose it's a little bit arbitrary that we could select just about anything that we wanted to be P. I think I want to look at other solutions to other problems to try to see how they decide what P is going to be. So that's going to be done in the next class. We're going to try to make that a little bit more clear. But let's continue on here, where we figured out that the distance between the 2 points after establishing this triangle. I think this triangle is relatively arbitrarily decided. That's my impression. But let's see what we get here. We measure or calculate the change in the angle, right? So that change in the angle, by the way, is really going to be the change in the angle of A1 B1 to A2 B2. Right in here. So so for the left side dyad here, we use the free choice strategy right here. Okay, so we're going to say that we have we know this length z, and we know its position phi. Right, that's what we chose to be for the triangle, or however the triangle was arrived at when we got this p. And then this beta 38.4, we measure that from the graphical approach. So these points aren't completely independent. They're very similar to each other. But I think we do have some amount of free choice about where where it's going to go. Right, where O2 will land, right? Remember that we could select it in the graphical choice along a line. So that's going to, in essence, help us to decide where this leg is going to be. Okay, so we figure out what the coordinates of Z1 and the X and the Y are going to be. Right, so that's going to be this right here, and so we could find now we're going to find the magnitude and direction of W. Right, so that this is part of that strategy too for the left hand side. So we have that A, B, C, D, E, and F right here, and from that we're able to find the locations of W right there. Right, and I believe that means that that's going to be also going to be the equal to the O2, if you will, by way of doing this. And I'm trying to assist because if you take a look at example 5.1 in the book, it doesn't give you a whole lot of actual answers in terms of how they came to these values. So I wanted to actually calculate the values myself. All right, so taking a look here, and we do want to get a length of this now. We get a length of 2.467, and we find that it's an angle of 71.57 degrees. So what we've done is we've figured out where O2 has to be for here. Okay, now we do the right-hand side. So we're going to use strategy 2 again. And we know this length, S, right here. And we know this angle because of the points that we picked, right? We picked this point on this triangle to get from P1 to P2. And now you also have this gamma 2, and once again that was measured from the graphical approach and has too many decimal places in it, so I have to fix that. Let me fix it. Yes, okay, good. I saw myself, it was still there for a second. All right, so from that, we're able to figure out the coordinates of S1 and in the X and the Y. All right, good. Oh, excuse me. And now we get to link 4. We could figure out the magnitude and direction of O1. That's really our main thing to do. So we get A, B, C, and D, A, B, C, D, E, and F. A, B, C, D, E, F. And with that, we're able to find the X and the Y position of U. And so we have the magnitude and angle right here, which is going to be psi that we have right there. Okay, so we've been able to figure out that thing's position there. So, whoop. No, this was right, Diane. Come over here. All right. So link 3 is now just in between. That's just going to be Z minus S, right? So we could have actually found that all the way along right there. Could also be found from the law of cosines, but yeah, we just found what that position vector would be. Yeah, okay, yeah, to find out that from our origin right here. Sure. Okay, and so we get the magnitude and direction of this, and so now if we want to get the ground link, all we need to do is solve that little loop right there. So we could do just the x's, the sum of the x's and the sum of the y's, and that's going to give us this loop, and we're going to be able to get the length and the angle. So to summarize, here's the ground link. We just found that right there. We have the crank. That ends up being the longest one. We got the coupler. That's this angle right here. And then we have the rocker, this length and angle. And we check for Grashof, and we see that it's non-Grashof, but that's okay. It doesn't matter. This doesn't need to do a full rotation for one thing. We want to make sure that it can move between the two spots, but it looks like it's a pretty good candidate to move between the two spots. We also want to take a look at the transmission angle, be worthwhile. So we can see what that's going to be, and of course that's just going to be the angle that's formed in between the coupler and the rocker. And since it is less than 90 degrees, it's not acceptable. That's funny. Transmission angle is always less than 90 degrees. I don't know. I have a problem with that. I don't know. I think it is acceptable. But then the final transmission angle right there is, I don't know why it says since it's less, it's not acceptable. I wrote that many years ago. I don't know why it is. I'm going to double check on that. The final transmission angle right here. Since this is less than 90 degrees. Oh, I see. Okay. Since it's less than 90 degrees, it equals the transmission angle. And they're saying that that's not an acceptable. It's because it's less than 45. That's why. Because it's less than 45, that's why it's not acceptable. It'd be better if it was more than 45. So we might want to go back and revisit these numbers. Some of the numbers were based on choices we made, especially the beta. Or I don't know if I think it was beta. It was a beta 1. I'm trying to remember. No, it was gamma. Gamma on this one might have influenced where that's going to be. So just be aware of that. And then, see, this is a good candidate for a spreadsheet. And if I can make a spreadsheet out of this, I will make a spreadsheet out of anything I possibly can. So you can see that I went down. I'm not sure why I decided to repeat the same 3 things over in the top, right and left. But I just kind of treated it like the left-hand side and the right-hand side. So I had my A, B, C, D, E, and F. I went ahead and put the equations in there. I got my W1X, W1Y put down in there, so I can get my crank, and then I can find my coupler. Do the same thing over on the right-hand side, and I have my U, which is going to be the rocker. And then I also can find the ground down below, and then I can do my Grashof check. And I'm not 100% sure if I just put this field in as saying non-Grashof here, because I observed it, or if maybe I made that as an if-then statement. We'll take a look and see here in a second. And then I also put the transmission angles by taking the theta 3 versus the theta 4. In both situations. Did I do it in both situations? That's interesting. So let me take a look at that here, and I have it up. Alright, so here is example right here. And no, I just wrote in non-Grashof, and I have that angle right in there. What is this angle right here? Okay. Oh yeah, I'm adding in the beta and the gamma right in there, because that's going to be the new angle right after it's moved over. Yep. So the new angle is this psi plus gamma is going to be, that's going to be the theta 4 in the new position, and then this is going to be theta plus, did I say psi? I meant sigma plus gamma, and then theta plus beta. Theta plus beta, that rhymes, that's nice. That we're going to have, this is going to be theta 3. All right, and then I put you down. Come back. All right, so for 2 position, this is MATLAB. So I think I've given you this, which was very nice to me, because I was thinking of like making people do this as an assignment, but it was a lot easier. It would have been a lot easier than the other ones. I'm going to have you try to use this Excel and MATLAB to solve a problem for which I give you the solution. And then maybe try to get a new one. I don't know. It's tough to pick a new problem that's not going to have problems. But so we have, okay, so in my MATLAB code, I'm bolding stuff where it's a number, and maybe I should put all those numbers like in the input in the beginning, or have them in the code be something that you would input. But I like to have it all in one place up at the top. But here's our left strategy. So some things that we need to know that we measure. So these are like inputs, whereas we could probably have other things to adapt this code for the actual situation that you would want to be put in there. But we do our Z's, and here's the A. And so here's the left-hand side, that A, B, C, D, E, and F. And so here we find the positions, and of the W's, and we find the magnitude, and we also find the angle. I probably should have put atan 2 instead for this. I think that's also a MATLAB code. It's an important thing to note. Right-hand side strategy. Once again, some of these things maybe we should have put in as as inputs in the beginning. These are things that we know, constants. I like to have them separate in the code, not built within the code. But we find the position of S right there, and then we have AR, BR, CR, DR, ER, and FR, right? Because we're using strategy 2, and we're able to find the position of U right here, and we get the magnitude and the angles that we care about, and then we get the coupler, and we get its length, and then we get the ground, and we're able to get its length. So there you go. That is example 5.1. It's not as exciting as it could be, but it's it's better than trying to read the book. Tell you that much.